Alright, hey guys, and welcome to a brief little mini-series. I'm not sure if it's going to be brief, but it's going to be a mini-series where I talk about and sort of show off some really basic processor design and some general circuit design and stuff like that. So basically the goal is to build a 32-bit working CPU that can run basic programs for memory and produce an output that way. This can be done in the Logisim program, which is a circuit logic simulator, which is kind of explanatory in the name. So when you look at a CPU, one of the main and biggest functions of the CPU is to perform addition and logic. We'll talk about storage and how CPUs store data, but at a very basic level, we should go ahead and start working on more of the addition and subtraction, multiplication, division, that sort of thing. The very basics of which addition and subtraction are done by adders. And to create adders, which are inside of the ALU, the arithmetic logic unit, you're going to need to go ahead and build your own circuits, right? Technically, Logisim actually has pre-built things here where I can do an adder, subtractor, multiply, divide, negate, compare, shift, bit add, and all these different things. But what we're going to be doing is working on showing off what the actual circuit looks like when you're designing it. So I'm going to go ahead and create a new circuit here. We're going to call it actually we're going to call it ALU because we're talking about arithmetic logic. Sorry, I'm still not quite used to the keyboard. ALU 1B FA. And what does this mean? This is an arithmetic logic unit for 1 byte, and it's going to be a full add. And it's pretty simple. You take ALU 1B FA, and we're going to create that. So, go ahead and get into the circuit here. What do you want? Here we go. Okay. Now that we are switched over here, we're going to start working with gates and wiring. Those are really the two things that we're going to be using for the most part. We might need to use multiplexers, mainly because of the fact that they're just very useful to begin with. Although I could probably roll my own design made out of these gates at some point. So we're going to start off by creating 2 pins, and pins are basic inputs. Basically, we're going to have them here and here. We're going to name this one A. We're going to name this one B. So this is input A and input B. Pretty simple to understand. And what we're going to go ahead and do is, so we're also going to define another input up here. And we're going to call it CFN, which is for the carry flag. Now the carry flag, what the? Select value. Oh, so for the carry flag is responsible for determining what the output basically taking in the output of the last carry and basically saying, hey, we need to carry over a 1 into the next position. And that's what the CFN does. Furthermore, we're going to actually have another pin, but this time we're going to set it over here as an output. Now, I'm not sure, is this facing, this should be facing south. And then this one should be facing north. And it's an output, and this one is going to be CF out. So it's going to be if we need to carry out. And we're going to put that on the south side. And the last thing, of course, is going to be probably the most important, which is the result, which is going to be R. And we're going to put it on the east side. It's an output. And it's facing west. Cool, so now that we have this basic idea of what our inputs and what our outputs are, we need to devise the logic to go ahead and actually get those inputs and outputs. So, in order to determine what the output here is going to be, is for the CF out. For the carry flag, we're going to know that if carry flag in comes in, and the result is adding 1 here, we're going to have to go ahead and set the carry flag out. additionally, if A and B are set here, we're also going to have to do a carry flag out. So knowing that, knowing those two conditions, we can go ahead and say, let's get an AND gate here going with two inputs, face it southwards. We're going to say that if this and this, then that, right? So if A, I'm not sure where the little nubbin is. I think that's correct. Yeah, that's connected. And B are true. So if A and B are true, so if bit 1 and bit 2 are true, we're going to go ahead and say, hey, we should probably make a carry flag. And we can carry it out. So this is one part of the logic here, to get CF out. Another part of the logic here is going to be getting the actual addition. So to get the actual addition, we're going to go ahead and take an XOR gate here. We're going to take two inputs, and we're going to take the XOR and connect A and B to it. Now, what does XOR do? It's an exclusive OR operator, which means that if X, so if A is true, then it's true. If B is true, it's true. If A and B are true, then it's false. And so it's basically exclusive OR, so that's pretty much the explanation of how that works. I'll move that forward one. Cool, so now that we have that, we'll have an output here. And this output will be off right now, because 1 and 1 are true. If it's not, if it's only one of them, then it's going to be true. And this kind of makes sense when you start thinking about it, because basically the addition of 0 plus 0 is 0. If the addition is 0 plus 1, it's 1. If it's 1 plus 1, you're going to carry, and it's 0 in this position, and it's 1, 0 in the next position, which is the CF out, and the carry flag goes into the next position. This is a basic ripple carry design. There's also a way of basically somewhat pre-computing it and figuring out when carriers are going to be done, and it's very useful in real-life circuit design for more efficient output. In this case, I don't think it's going to matter too much because it's being simulated on a computer, and we're not going to be running it at speeds that are very significant. Now, what about carry flag in? So if we're going to take the carry flag in, we need to actually factor that into our result. We can't just say, oh, hey, it's got to work, right? If the carry flag is on, we need to at least acknowledge that. And what we can actually do is really simple, is that, hey, if it's on, then let's get another XOR. Take that, take CF in, and pass it together, and then pass out the results out of this. Now this is already correct, but we also have to consider it for CF out. Before I do that, I'll go ahead and show that if I turn on the carry flag in, it's going to be on here. If I've got, so basically it's just adding another 1 to this position. So if we have 1 plus 1, it becomes 0. So we had the byte 0, 1 plus the byte 0, 1, it becomes 1, 0. Well, what happens if, let's say, there was something before that, and we pass in the carry flag in? Well, hey, now there's another 1, so 1 plus 0, 1 plus 0, 1 plus 0, 1 is going to be 1, 1 as the output. So it creates a CF out here as 1, and 1 over here. Now, what it doesn't go ahead and cover is what happens if we had A and B 0, 1. So this is actually 1, 1, which is going to end up 1 plus 1, which is going to be 1, 0. And now you see the issue. It doesn't actually add here. So the actual way to solve this would probably be taking an OR gate with 2 inputs and then going ahead and doing it facing south. Output goes here. And we're going to go ahead and delete this over here. And we're going to go ahead and take CF out. And just throw it in here. And take it down from CF in. 1 over. and use that to determine what CF out is. Now this way, if this is on, then of course it's going to carry through, right? And then if this is out on, it's going to carry out. This carries out. And if we go ahead and do this and this, it carries out. And if we just have this, this actually shouldn't carry out. So I'm taking it from the wrong side here. I should actually be taking it from the output value of this. It's going to be another AND, I believe. And it should be 5, 2. And then we're going to take another AND here. Connect it down here. I want to somewhat move it over. Don't mind the siren in the background. And then we're going to go ahead and connect it. I'm not quite sure what's going on here. Go ahead and connect it out over to here as one of the arguments, and this one as another argument, meaning that if these two are true, then it should be a CF out. So that way we don't have the issue now. If we turn on 1, it does not actually turn on the CF out. There's going to be 1 here. That works. 1, 1. That will cause a carry. And then 1, 1 causes a carry. And then adding another one here displays the correct result. So now that we have this basic adder right here, we're going to go ahead and pretty much make it a nice little module so that we can use it in the future. I'm going to go ahead and actually save it here. And then we're going to go to this little module view. And now that we have this, let's go ahead and, oops, that's not what I wanted. Define the box. This is something a little bigger so that we can, actually tell what's going on. This is what temperature is facing. And then this is the output. So if I go ahead and click on it here, it shows in the bottom corner what part it is. So in this case, this is the output result. Down here is going to be essentially the CF out. I'm going to shrink this actually so that's centered. And then we're going to take the other one up here. This is CF in. So we're going to take CF in. And then we're going to take B down here and A over here. And there we go. We got a simple 1-bit adder. And then we can go ahead and use it as a component in our other parts of the ALU. So I hope you guys have enjoyed this tutorial, and I will be back with another one on the basics of the arithmetic logic unit, doing a adder for multiple bits. We're going to go ahead and string them together in 4 bits, 8 bits, 16 bits, 32 bits. Doesn't really matter because we can always just keep stringing them together.